final, it's more going to be 17, 18, 19, 20 is more going to be plug and chug and major concept questions. Like I expect you to know, for instance, exactly what let's say the zeroth law of thermodynamics is, or exactly what the first law of thermodynamics is. Maybe various versions of the second law of thermodynamics. You should be able to state those or identify them. Like if I gave you a list of a bunch of different sentences, could you identify the ones that were the first law? Could you identify the ones that were the second law? Could you identify the ones that were the zeroth law? Your book even mentions the third law of thermodynamics, but I'm not going to touch that. But I will expect you to have read chapter 20 pretty thoroughly, so you'll have some understanding of it. As far as the work goes in the plug and chug, they would be more along the lines of, can you, for instance, use the ideal gas law to solve for pressure? Or can you use one of those versions of the ideal gas law, either the PV over T equals PV over T, or PV equals nRT, or PV equals nKT, to solve for temperature, or solve for the number of moles, or solve for the number of atoms. Those are pretty straightforward problems. Solving for the velocity of a particular molecule in a particular sample of gas at a certain temperature. We've learned how to do that. I basically derived that with the kinetic theory, which you can either look at as me deriving the ideal gas law, or you can look at it as us using the kinetic theory to derive the average random kinetic energy of the molecules or atoms making up a substance. You should be able to calculate the efficiency of a Carnot engine, and you should be able to calculate the coefficient of performance for a heat pump, or for a air conditioner, or actually I meant a refrigerator, that sort of thing. And those are, like I said, mostly plug and chug stuff, like the examples that you see in the book, maybe even easier than the examples you see in the book. So when you start taking these last practice tests, you are actually prepping quite well, and way beyond what's necessary for the final. So it's really good background material. Okay. Anybody have any questions on any of the past stuff from 17, 18, 19, or 20, or even the stuff 21 through 31? I would also say you guys should know, for instance, what's Gauss's law, what's Ampere's law, what's Faraday's law, what law tells us that there's no magnetic monopoles, and you should be able to, identify those in equation form. So that's why your equation sheet's actually allowed to have equations on it, but you're not allowed to have sentences. You're not allowed to have names of equations, stuff like that. And when you take the online version of the test, you're supposed to do the Respondus lockdown browser and the Respondus monitor, and in that you're supposed to show me your entire front and back of your equation sheet, so that I can know they're not on there. You're going to be showing me your ID, of course, too, your photo ID. You're welcome to cover up the identifying number, like if it's got a social security number or driver's license number on it. That might be something you don't want your instructor to know. I don't know why. I wouldn't do anything with it, but there may be some potential danger. There definitely would be if you were doing a social security card, but that doesn't have a photo on it. So you're supposed to show me your ID next to your face so I can compare the two. And actually they have monitors as well that do that stuff. So that's how that's going to go. Since we're a Tuesday, Thursday class, our last day of class officially is Thursday of next week. And I never put the exam on the last day because I like to have that last day in the event of an emergency or something like that. Someone has to do a makeup. That's why your exam will be on Tuesday. And you're allowed to start as early as, well, in general, I try to say you're allowed to start as early as 4:35. And you're not allowed to start any later than 5:20. Obviously, I've got one student that requested something different, and I got another student that's planning on taking a test at the testing center, I think, at a different time as well. So those tests either will be different, or some other situations are going to go on with that. Anybody have any questions? All right. Well,
I have another question.
go for it,
I'm
Maya.
sorry. So as far as us like showing our work on the pages, are you gonna want us to send you those like our work in like
That's
separately or show the
possible.
camera or anything?
Yeah, that's possible. So sometimes I'll have one or two questions in the whole test that I'll ask you to turn in. And actually, I just discovered Respondus has the ability to do that inside Respondus, so it can literally take the pictures for you, and you can just upload them straight there. If I do that, it'll be there. So you definitely should read your questions when you go to work them, and some of them might say, "I need to see this." For instance, in 242, as I've been harping on the whole semester, you should be able to use either Coulomb's law or Gauss's law, normally Gauss's law, to calculate an electric field using the symmetries and all that good stuff of a very specific symmetric body, whether it be spherically symmetric, cylindrically symmetric, or infinitely planar. Those are sort of the scenarios in which you can apply Gauss's law the weird way we did it. You should be able to do that. Then you should be able to use V equals the negative integral of E dot dl to calculate the voltage difference between two parts of, say, a charged object that's creating electric fields between the two parts. And then you should be able to use C equals Q over V to calculate the capacitance. That three-step problem is sort of one of the hallmarks of this course, and it's something you should be able to accomplish. Additionally, there's another one I've been harping on. You should be able to use the law of Biot-Savart or the law, Ampere's law, one of the two, usually Ampere's law, to calculate the magnetic field of a particular, particularly symmetric situation, particularly symmetric so that you could actually do that nasty integral that is Biot-Savart, or particularly symmetric so that you can use Ampere's law in that weird way that we use it to compute the magnetic field. Then once you have the magnetic field, you're supposed to be able to use the definition of magnetic flux, which is the integral of B dot dA, to calculate the flux. And in that case, you're looking for a flux. You're looking for a surface that the magnetic field is essentially going to be uniform over the whole surface and will be, in fact, perpendicular to the surface, which means it's parallel to the dA vector. So that's the second part of that three-step problem. And then after you have the magnetic flux, you're supposed to use L, the self-inductance, is equal to N, the number of coils, times the magnetic flux phi divided by I, the current. And you use that to calculate the self-inductance, or just inductance as we call it. So that's the second three-step problem you're supposed to be able to do. Obviously, you're also supposed to know the parts of the electromagnetic spectrum. I taught you guys the goofy mnemonic I use, and sort of paying homage to Rush Limbaugh, who, though I have my issues with him, I owe him all my interest in politics and stuff like that, because he has been very, at least well spoken on it. So I've really enjoyed watching him up until he died, or well, was initially watching him and then listening to him up until he died. So it's great excess undermines various industries, Marxism rules. That's the mnemonic that I get you guys to use to know the parts of the electromagnetic spectrum. You should not only know them, great excess undermines various industries, Marxism rules, great excess undermines various industries, Marxism rules. You should know them in that order, or some other order, or with some other mnemonic that you use. But in that order, that's basically going from high energy to low energy, which is the same thing as high frequency to low frequency, which is the same thing as high temperature to low temperature, which is the same thing as short wavelength to large wavelength. And then finally, because we did it in that way, great excess undermines various industries, Marxism rules. You can't use Roy G. Biv to break up the visual. You have to use Vib-Gyor, V-I-B-G-Y-O-R. So just keep that in mind. Okay. All of those types of radiation, gamma rays, ultraviolet, visible, infrared, microwaves, and radio waves, all of those, and yeah, I think I got them all. Infrared, visible, ultraviolet. Yeah, I don't think I forgot anything, but all of them are what we call electromagnetic radiation. That means they're an electric field oscillating in one plane For instance, if the electric field oscillates up and down, it's vertically polarized. If it oscillates left and right, it's horizontally polarized. Normally, it's just at some random direction, and then the magnetic field is perpendicular to the electric field. So that orbiting plane or that oscillating plane is perpendicular to the electric field plane, and both of those planes are perpendicular to the velocity in such a way that the right-hand rule, E cross B, gives you the direction of V, the velocity. So that's all the stuff you're supposed to know. V equals F times lambda, the baby wave equation, and all that good stuff. So anybody have any questions about that stuff before I go on with the 19 and 20 stuff? Okay, that's a pretty good list of topics to remind you of. Just, basically, you should always, if you have a whole chapter dedicated to a particular principle or law or rule or something like that, there's a good chance that your instructor might think they're being really generous by asking you to state that rule or that law or that equation or something like that. So that's why I tell you, yeah, you need to know what Gauss's law is, be able to write it down at the drop of a hat, or you should be able to do the same thing with Ampere's law and Faraday's law, and then there is no magnetic monopoles law and all that good stuff, as well as, of course, Lenz's law. You should know that one. You should, even though this wasn't covered this semester but covered last semester, you should know Newton's first law of motion, Newton's second law of motion, Newton's third law of motion. I would not go as far as to say you should know Kepler's laws at this point, but you should also know the Kirchhoff loop rule and the Kirchhoff's junction rule. That's pretty much, Eli the Iceman, you should know that. So any questions? All right, well, let's get cracking. So we've done this area where we basically did ideal gas law. We know how to, I've shown you how to convert temperatures between Fahrenheit and Celsius, the quote unquote pedagogic way, i.e. the way that, well, i.e. by the way means in other words, that's a good description of it anyways. I period, E period, comma is the way you write that. And E period, G period, comma is the way you write that. They're both Latin phrases, by the way. I read IE as in other words, and I read EG as for example. I think it's example gratia or something like that. But the main thing is I use that stuff and I feel bad because not everybody knows it. But anyways, basically you should know, hang on, I didn't forget what I was talking about because I went on a side tangent with the with the rules on Latin and all that stuff. Oh yeah, I remember what it is. Okay, so you definitely should know how to convert between Fahrenheit and Celsius, but I told you that way that's pedagogically more helpful, where you first consider the temperature that they give you and figure out how far that is from some important temperature where you know both scales. So for instance, the boiling point of water, is 212 Fahrenheit and 100 Celsius, or the freezing point of water, is 0 Celsius or 32 Fahrenheit. So you find out how far the temperature they gave you is from freezing, and you basically, subtract, so you get the difference between it and freezing or between it and boiling. And then you use that conversion factor that basically says 180 Fahrenheit degrees is equal to 100 Celsius degrees, or you can flip it over and say 100 Celsius degrees over 180 Fahrenheit, but it also reduces to 18 over 10 or 10 over 18. That also reduces to 9 over 5 or 5 over 9. And you have to, of course, do a unit conversion there. Then once you've got how far it is from freezing in that new temperature scale, then you have to add back what that other value is. So if you're doing it to freezing and you're going to Celsius, you don't have to add anything because you're just adding 0. But if you're going to Fahrenheit, you have to add 32 because that's freezing. Similarly, if you're going to the boiling point and you're going to Celsius scale, you have to add 100 to it. If you're going to freezing, to the boiling point, and you're going to Fahrenheit, then you have to add 212 to it. So that's the way we recommend. Then you need to know, of course, how to convert Kelvin to Celsius and Celsius to Kelvin. I don't care about your ability to convert to Rankine or even knowing Rankine. I won't ask you that, but I always cover it for good reason. Then you also need to know how to convert pressures from gauge pressures to total pressure. You need to know what an atmospheric pressure is, as well as what it is in Pascal, what it is in torr, what it is in millimeters of mercury, and maybe even what it is in PSI. That's all so that you can use PV equals nRT, because the ideal gas law only works with the Kelvin temperature and only works with with total pressure, not gauge pressure. So that's pretty much what we did in chapters 17 and 18, including calculating the average kinetic energy, the average translational kinetic energy of the atoms or molecules in a gas at a given temperature. Yes, someone raised their hand.
I'm not sure if you already went over this, but the practice tests, a few of the practice tests are their last day due, I guess, was December 6th, 2022.
Oh, okay. Well, they're not even supposed to be showing if they got the wrong dates on it. I will check them tonight, but I'm supposed to have the practice tests for the last test, as well as the practice test, 2 versions for the final, one of which is Respondus, so you can learn how to use Respondus, make sure your computer's up to date and all that good stuff, for Respondus Lockdown Browser and Respondus Monitor. And then the other one's just the one you're supposed to take a bunch of times, but all of those are supposed to have the right dates. I will check them as soon as I leave here. If anything has the wrong date, it shouldn't be available, and it's just probably left over from an old course. You do not have to do it. Okay. Additionally, when you look in the homeworks, the only chapters that are required of you for this semester, I'm going to type them right here in the chat. The only chapters are chapters 21 to 31 and 17 to 20 are only chapters you are required to complete. All others are extra credit. So I just sent that out just to make sure everybody's on the same page. 21 to 31 is fair game, 17 to 20 is fair game, and I'm even covering 17 to 20 in a light way. Okay. Thanks for letting me know that, though. Was that Michael?
Yeah.
Okay. Thanks for letting me know that. I'll check that and make sure. I tell you what I did do in one class. I don't think it was this one, but I actually completely copied the wrong test. And not only that, I had like 200 points in that test instead of 100. And instead of it being chapters A, B, and C, it was like chapters Q, X, and Y. So that did happen just this semester. So I will definitely check it out and look for it. If you see any practice tests or anything like that look fishy, like they're doing something fishy, let me know. But do be advised, all my tests are always comprehensive. So it's not unreasonable to see 1 out of 10 or 1 or 2 out of 13 to 15 problems be from previous chapters. And even if it's a test on chapters 17, 18, 19, 20, there is some likelihood that you'll have a couple questions from chapters 21 through 31. All right, so I guess we're ready to roll now. So what I wanted to do is start off with a little bit of calorimetry problems. I will remind you of the diagram that I was able to draw for you guys. And this one was specifically for water, so you have an understanding how matter behaves. So what I'm going to do is I'm going to hit share screen, and we're going to pray that it works, because that'd be awesome. Oh, great. Good, somebody's calling me. That was super helpful. Stupid Rocket Mortgage. Never calling them fools again. All right. All right, so now I'm going for it. I think I've got everything worked out where it works now. So let's see. May or may not be working, but it's going slow either way. There it is. And y'all can see this, yes?
Yeah.
All right, cool. That scares me. Okay, so the one thing I showed you guys before was I showed you how temperature it could be plotted on the vertical axis, and heat put in could be plotted on the horizontal axis. And that was specifically for, say, water. And we might even, given what I'm talking about here, we might even say it's a gram of water. Okay. So what we found happens when we're doing such a thing is that the water, when it's at its coldest, is of course in a solid state under almost all conditions. And the graph actually looks like, let's say, this. Okay. Now, once it reaches 0 degrees, what happens is it starts to melt. Now, when it starts to melt, basically all the water stays a set temperature, specifically 0 if it's at 1 atmosphere, and it stays that way until you can break up all the little bonds that are holding the molecules of water together, molecules of water together in the lattice that water has. So that takes essentially an additional 79.7 calories until all those bonds are broke. And that's called the latent. It's in general called latent heat, but in this case, it's of fusion. And if you're going from the liquid state into the solid state, that's heat that's put out. If you're going the other way around, that's heat that you have to put in to break it up. And I've told you, for instance, about the strawberry festival and stuff like that. Once you start growing strawberries, freezing temperatures can damage them. So what farmers do when there's a freezing temperature night coming is they'll spray them with water. And then that water, as the temperature gets lower and lower and lower, the water will start to get colder and colder and colder. And what will happen is it'll ultimately freeze, which you might think is bad, but it freezes and ends up locking it at a temperature of 0 degrees Celsius. And not only that, it gives it that little latent heat of fusion boost of heat. So it actually gives off a little bit more heat to the strawberry. So the strawberry, even if it had gotten below freezing before that, now it's probably going to be a little bit closer to freezing and slightly even above freezing. And it's got this nice protective layer of almost like a coat or a burqa or something, or excuse me, I said burqa, a parka. That's an entirely different thing. A parka over it. So once that heat is put in, by the way, you can then begin raising the temperature with the famous equation Q equals MC delta T. And then what's going to happen is, again, assuming 1 atmosphere of pressure, you're going to reach 100 degrees Celsius. And at that point, it's going to be yet another latent heat that has to be overcome. But in this case, the latent heat is huge. I think it is 539. I think. Let's double check that if I can. Actually, I'm just going to go with it. I'll say this is on the order of 539 calories. Y'all can look it up in the book if you want. But the main thing is that's, again, a latent heat, but it's a latent heat of vaporization. And this one is helpful to us because when we sweat, that sweat is mostly water. It's got some salt in it and stuff like that, but it is mostly water. And as the sweat gets on your body, then what will happen is the air temperature will cause it to reach close to the 100 degrees Celsius, and possibly just minute amount of it, even if the outside temperature is not 100 degrees, some of it's going to go into vapor just as a result of the fact that some of it just makes it to vapor because of the statistical randomness of the velocities of the particles. So when we do that, what happens is the water will, in some cases or in small amounts, will change from the liquid state to the gaseous state. And in that case, they're actually stealing a little chunk of heat from your body. And that chunk of heat is the latent heat of fusion. So that's the extra kick that the sweat gives us. Yes, the sweat cools us down because it comes out of our body and is ostensibly colder than our outside surface of our body that's actually subjected to the temperature. And then it's also going to, in fact, get cooler as the air touches it and all that good stuff. But it also gives out after it actually goes into the gaseous vapor state, then it's going to give off another little kick of heat. And then in that case, it's actually absorbing the heat and stealing it from your overheated body. Now, the slopes here are different, and that's because the slopes are based on Q equals MC delta T, and the specific heat is different for each of them. So in this area, you have Q is equal to MC delta T, and that's the same thing. And in this case, it would be water. And here we've got Q equals MC delta T, but in this case, it's ice. And then here we have Q equals MC delta T, and in this case, we have steam. So there's different specific heats for each of those. You can look them up. In fact, your book has a nice table that we can use as needed. And if I ask you to solve a problem like that, I obviously either have to give you the table or I have to give you the actual numbers. So that's sort of what we get from understanding that matter is made up of these small things that we once thought were indivisible, and therefore the ancient Greeks called them indivisible, which translates to atom, meaning a, not, and then tom, which means divisible, basically. So that's where we get the idea of the atom and all that good stuff. Now we know that the atom can, of course, be broken up and all that good stuff. So there's neat little calculations that we did earlier about, estimating the distance between two atoms. If we know the density, for instance, I think I did the one for copper. If you know the density of copper and you know the molecular weight of copper, you can use that to estimate how far the copper atoms are apart from each other. And that is, in some sense, the diameter of the copper atoms. Okay. So those are other problems that you can be expected to know how to do. Now that we have that, I'm going to give you a neat little problem. What I would like to do is I want to say work a problem. And here's the example. We're going to use calorimetry. And I'm going to ask you how much heat is required to raise the temperature. Oh, I don't know what happened there. The temperature of a, iron let's say 40.0 liter empty container from 10.0 degrees Celsius to 90.0 degrees Celsius. And part B, what if it was filled with 40.0 liters of water, also at 10.0 degrees Celsius. Okay, so what we have is basically a big container made out of iron. The container has a 40-liter capacity. And in fact, not only is it 40 liters in capacity that it holds, but in fact, it's actually, let me think about what its mass would be. I don't know if I want to, yeah, I'll use the density. Actually, no, I'm going to go ahead and give you the actual mass of the iron. Let's say the iron case, the iron container actually has a mass of, let's say, it's going to be 80.0 kilograms. Okay. So I'll just add that in there. It's a little different than the way I'd originally planned to solve this problem, but that's okay. It works, and actually might even make it a little more straightforward so you guys will get it better. So everybody understand what that problem is? Yes, Michael.
What is the 40T? Is that 40 tons?
No, that's 40 liters, and it's actually 40 dash liters, because when you write a thing like it's a thing with the name 40 liters, you're actually supposed to hyphenate between the number and the unit. So if I say a 40 liter container, it's 40 dash liter. Whereas if I say a container can hold 40 liters, then it's just 40 space liters. That makes sense? All right, so let's work on the solution. So in this case, what I always do, at least when I do calorimetry, I always do take the thing that's adding, that's losing heat, and I set that equal to the thing or things that are gaining heat. Your book often does delta Q equals 0. I don't like doing that specifically because the latent heats. Sometimes students get confused as to whether the latent heat should be positive or negative, and which direction you're going. You know, if you're going from steam to liquid or liquid to steam, which one's positive, which one's negative, or sublimating, that sort of thing. That's another latent heat. There's a latent heat of sublimation that CO2 has. But anyways, this case, we're just asked for the heat. So I just got to use a Q equals MC delta T. So in this case, I'm going to say part A, Q, iron, is going to be equal to the mass of the iron, which I've changed and decided to make it 40 kilograms. Now, what I happen to know is that the actual specific heat of iron is 450 joules per kilogram Celsius degree. Now, I would have to give you that if we're doing the problem on a test or anything. I just happen to know it off the top of my head, specifically because I've worked this problem recently, or a problem like it recently. So in this case, we're supposed to do T final minus T initial, because the equations, as you see up here, are Q equals MC delta T. When you do the heat added or heat loss equals heat gained that I was talking about earlier when we're doing calorimetry, in that case, you don't do a delta T. You just always do big number minus small number, so you always get a positive. So just keep that in mind. In this case, it's going to be 90.0 degrees Celsius minus 10.0 degrees Celsius, like so. And that's pretty straightforward. I'm going to say 80, and that 80 is actually probably pretty low for the actual mass of this, but still it's good enough. We'll say 80 times 450 times 90 minus 10 is another 80. So that's going to be 2.88 times 10 to the holy crap 6. And I'll carry one extra sig fig, which is a 0. That's 2.88 times 10 to the 6. And I think you can see that all the units canceled out except for the joule on top. So we can say Q for the iron alone is in fact 2.88 times 10 to the 6 joules. Now I can do part B, which is Q for the water. So Q H2O. In this case, the water's mass is actually, hopefully you guys know this. This is one thing everybody should know. If you want to be an engineer or you want to be a scientist, you really should know the density of water, and this is liquid water, not ice. Okay, but liquid water has a density of, and it's actually just a lot of wonderful numbers. That's why you should know it, because it's so easy to actually deal with. But it's basically 1 gram per milliliter, 1 gram per cubic centimeter, 1 kilogram per liter, or 1,000 kilograms per cubic meter. So those are things you should just know. So since this is 40 liters, I know it's 40 kilograms. So I'm going to put right here, well, I'm going to erase a bunch of stuff evidently because my iPad said I would. But anyways, this is going to be 40.0 kilograms. Now the specific heat, that's probably something you should also know, just like you should know the natural log of 2 and the natural log of 0.5. But for water, it's 4,186 joules per kilogram Celsius degree. Ice, by the way, is 2,100, whereas water is 4,186. I just wanted you to see that, yeah, indeed, the specific heats are different. And then finally, the same temperature change is going to be 90.0. Well, I should write disease Celsius. Yeah, I should write disease Celsius minus 10.0 degrees Celsius. This is going to give me a monstrous number, way bigger than that other one. So in this case, I'm going to say 40 times 4186 times 80. And oh crap, that's big. I'm going to say 13.40 or 13.40. That's giving 1 extra sig fig. 14, or excuse me, let's say 1.34. So, okay, 1.340 times 10 to the, oh my goodness, 1, 2, 3, 4, 5, 6, 7, 10 to the 7th joules. Now that's just to raise the temperature of the water. What we're really asking here in part B is what's the total heat required to raise the vat as well as the water. So I've got to add these two together. I'm going to say plus 288,000. And in this case, the total answer is Q total is equal to 1.62. Well, dang it, I hate it when it does that. Make me want to punch a baby. 1.628 times 10 to the 1, 2, 3, 4, 5, 6, 7. I shouldn't have had to check that, but just to be safe, I did anyways. So everybody understand how that was done? Does that make some sense to you guys? Okay, that was an unfortunate thing that just happened. I just wrote right over the 7 there. Let's see if I can undo that. Yeah, I can undo it because I got skills. Okay, now I'm going to do it again. I'm going to take a little curve here, do a little curve there. So no questions? All right, so that's the answer to part B. Now, let's do another example, another calorimetry example, only this time I'm going to make use of the latent heat. And what I'm going to try to do is give you some nice Southern culture. I'm going to give you some nice Southern culture about sweet tea. All right. Actually, that's not too far from my real voice and a lot of my family members. But sweet tea is sweet tea, and it turns out we like it really sweet. We like it really cold. So really sweet tea here in the South is supposed to be ice cold, and ideally you'd really want it to be 0 degrees Celsius. That would be ideal. But if you're in, say, the business of catering or for a restaurant or something, you make copious amounts of tea. Even Hardee's, for instance, has to make copious amounts of tea. So what I'm going to do is imagine a scenario where we've got some really hot tea, because the way you make tea, of course, is you take and boil water, and then you steep the tea bags in the water for some period of time. The way we do it, if we want tea, and I don't necessarily do the sugar thing, I drink mine with little or no sugar. But the main thing is, if you do want to put sugar in, you should do that while it's hot, and that's specifically because just like the air can absorb more water when the temperature is higher, other things, including water and tea, can absorb more sugar when the temperature is higher. So ideally, what you'd like to do is sweeten the tea while it's still hot. But you also need to make the tea a little stronger than you want, because we normally use ice to bring down the temperature. And if you use ice, a good fraction of that ice normally melts and waters it down. So your tea might come out, almost clear. So anyways, that's just some of the practical things to think about. So let's do this example. That's the worst looking thing I ever saw. So example. A 5.00 liter full container has 5.00 liters of tea in it at 95.0 degrees Celsius. Assume water is, or excuse me, assume tea is thermally equivalent to water. Now, this is not necessarily true. I've sort of done this assumption over and over and over again. And just last semester, I had a really good student of mine call me on it. And he's like, I don't think that's the case. And we'll come find out he's a cook in the Navy. And actually, he's a really smart guy anyway. So he probably would have thought about it on his own. But he's like, I'm pretty sure tea is quite different. I looked it up and I'm like, holy crap. The specific heat's off, the density's off, everything. But we're going to assume it's basically just tea with water without the sugar. And that'll make it a little better. So it's a pretty decent approximation. But that's what we have. We have 5 liters of water in a container, and our 5 liters of tea, which we're going to treat as water, in a container. And the tea actually has a mass, or excuse me, a temperature of 95.0 degrees Celsius, meaning we just finished boiling it. Okay. If we choose to cool the tea by adding 2.00 kilograms of ice at negative 10.0 degrees Celsius to it, will all of the ice melt? So that's part A. B, what will be the final temperature if we assume the cooling took place in an efficient calorimeter. So in other words, we're going to assume it's sort of like what we did in lab, which is we had a container, and that container had been used in such a way that it minimizes the loss of heat to the surroundings and stuff of that sort, and also minimizes the amount of heat that could come in from the surroundings. So we're going to assume that's 100% efficient. All that means is basically every bit of heat that is extracted from the hot tea is going to be absorbed by the ice so that none's lost. Okay, so we're going to go ahead and do solve this problem as follows. Does anybody have any questions about the problem? Okay, so this is where I told you your author tends to use delta Q equals 0, and that's fine. And if you do that, you've got to be sure to use delta T is equal to T final minus T initial. Sometimes that'll come out negative, sometimes that'll come out positive, but the main thing is you have to do T final minus T initial. The way I do it is you have to do big number minus small number, because I'm just saying, hey, 1, 2, 3, 5 things are losing heat. Like in your lab, for instance, the one thing was the little block of metal that we had stuck in boiling hot water. That was the one and only thing that was losing heat. But there were a couple of things actually gaining heat, and that was the water in the calorimeter cup and the inner calorimeter cup as well. So you've got to take account of all the things that are losing heat and all the things that are gaining heat, and put them on the energy that they're losing on their respective side. So everything that's losing heat should be on one side, and all the signs should be positive, and everything that's gaining heat should be put on the other side, and everything should be positive. So when I do that, what I get is, and I'm going to make use again of the thing I told you we should know, which is the density of water. And since I'm assuming T is thermally water, then 5 liters of T is essentially 5 kilograms of water. So I'm going to say Q loss is equal to Q gained. But first off, what I want to do is I need to find out whether this T is actually hot enough to melt the whole ice, or is the ice massive enough and cold enough to bring all the T to 0 degrees Celsius. That would be the ideal scenario for us Southerners who like our iced tea to be really cold and iced tea. And that is sort of the holy grail of tea. But let's check that first. So part A. What I'm going to do is I'm going to say Q for melting. Okay, so this is not Q loss equals Q gain. This is just the total heat required to melt the ice. So the ice is given to us at -10 degrees Celsius. So we first got to bring that up to 0 degrees Celsius so it can begin to melt. And then we got to add the latent heat of fusion. Words of the wise, the heat of fusion is not 79.7 like I put on the previous graph. That's only if you're using calories, which I could do, but I'll just convert it. So anyways, we'll say it because I don't remember the number in joules off the top of my head. Well, actually, I remember the C, but not for ice. Actually, yeah, I do remember the C for ice. So anyways, we have MC delta T. That's one version that we have to use. And that's just the heat required to change the temperature of an object of mass M with a specific heat C by an amount delta T. And then we've got Q is equal to M times L, where L is the heat of fusion, heat of vaporization, heat of sublimation, that sort of thing. So first off, I'm going to bring the water up to the ice up to 0 degrees Celsius. So I'm going to take the ice, which is 2 kilograms, and actually, I'm going to convert that to grams. That's what I'm going to do. That way I can use calories. I like that. So 2,000 grams, and that is actually 1 extra sig fig. 2,000 grams. Now the specific heat of ice, sadly enough, I happen to have known in not in degrees Celsius, or excuse me, not in calories, but rather in joules, which was 2,100. So that means I gotta convert the stupid thing unless I can pull this table up quick enough, which it looks like I cannot. I'm trying to do it really quickly here. Come on, come on, come on. There it is. Specific heat. Let's see there. Specific heat of ice. I'm pulling it up, pulling it up, pulling it up. Is 0.5. And that's calories per gram of degree Celsius. So 0.5. I'm going to pretend like that's 3 sig figs, but I really think they only gave us 2 sig figs. So anyways, that's calories per gram Celsius degree. And then, of course, I've got to do big number minus small number. So the big number is 0. And then I'll go minus, and that's 0 degrees Celsius, of course, minus negative 10.0 degrees Celsius. That's part of the heat. Now, I also, once I get it up to 0, I then got to convert it all from the liquid state, or excuse me, from the solid state to the liquid state. So that's going to take an additional amount of heat given by the heat of vaporization, or excuse me, the heat of fusion. And I will pull that up. And what I found was the heat of vaporization was 79.7 calories per gram. So I'm going to do 2,000 grams times 79.7 calories per gram. That's going to give me the total number of calories. So when I do that math, I'm going to say 2,000 times 0.5 times 10. I don't even need to use a calculator for that. That gives me 10,000. And then I'm going to say plus 2,000 times 79.7. And that gives me 169,400. 169,400. And of course, that's 4 sig figs. So all 3 of these are not good. And that's calories. And one of the things I didn't really mention, but if you look in the opening of chapter 19, there's something that we've always used, probably if you've had chemistry at all yet, you've used it as a conversion factor, but it really is way bigger than a conversion factor. Basically, Joule did an experiment that was monumental in that we thought energy that you use to heat things up was a very specific thing called caloric. And it was like a fluid that flowed from hot things to cold things and stuff like that. Whereas we thought energy that you use, mechanical energy, like potential energy, kinetic energy, that sort of stuff, we thought that was an entirely different form. In fact, we measured that in joules. So what Joule did was he took basically a mass and hung it at a height, and he allowed it to fall. The rope that it was tied to was actually tied to it, ran over a pulley, and then went over to a axle and caused that axle to spin. That axle was an axle for a propeller inside of a container of water. And you know, if a propeller spins in a container of water, it's going to speed up the molecules in the water. Now, that's going to speed them up in a very uniform way. So that's not really changing the temperature. But because all those molecules are going faster, they're eventually going to reach the point where they collide so much that the net kinetic energy of, and I mean the random net kinetic energy of the molecules will then be higher. And that is a measure of temperature. So he just watched the temperature gauge, and he could then relate MC delta T to MGH, which is the potential energy. And what he found, in fact, was 4.186 calories, or excuse me, calories is equal to 1 joule. Now I'm going to double check that because right now I just drew a blank and I'm starting to think that I might have gotten it backwards. And not only that, I'm thinking about kilojoules, 4.186. Yeah, I did get it backwards. That was close. That was a close call. I almost let you see me be an idiot. Oh crap, it's already there. It's 4.186 joules is equal to 1 calorie. So what I'm saying is, yes, that is still a conversion factor, but it's important to understand that that was a monumental discovery in physics, and that allows us to do neat things like account for the loss of kinetic energy of a bullet that is shot through a tree by assuming it actually partly raised the temperature of the tree. So this also means 4.186 kilojoules is equal to 1 kilocalorie. And 1 kilocalorie, by the way, we often abbreviate like this. We say it's 1 calorie with a capital C. And that's the dietary calorie that we use as well. So when we say calorie and we're talking about Oreos, for instance, we mean kilocalories are calories with a capital L. So that's part of the reason why it's so hard to lose weight, because you're dealing with kilocalories. The good news is the body is only about 20% efficient. So if you need to put out, 700 joules to climb a mountain or to climb some fraction of a mountain, then in fact, you have to put out so much heat or so much energy that only 0.2% of that energy will be 700 joules. So the rest is actually burnt energy. So you're actually losing a little bit more than just the straight 700 because you're burning so many calories, because only 20% of that goes to the actual climbing. All right, now that I have that, I can actually convert this back and forth between calories and joules. The other thing I need to do is now I need to see, well, how much heat does it take away from the T to bring it down to 0 degrees Celsius. So if I did that, let's see, we're going to say Q T T to 0. Okay. So in this case, it's going to be the mass of the T, which we're treating as water. So that's going to be 5,000 grams times the specific heat of water, which is 1.00 calories per gram Celsius degree, times, in this case, 95.0 degrees. Notice I'm doing big number minus small number minus 0.0 degrees, which would be what it have to be if I just got it to 0. Now, there's some probability that the ice is so much and takes so much energy that it might actually not only bring the T down to 0, maybe it could actually try to freeze all the T and bring it down to below 0. That's not going to happen, but that's a possibility. But if this number is smaller than the number we just calculated, then we're golden. We know it's not going to do it. So let's do this number. So we're going to do 5,000 times 1. I don't even have to put that in the calculator because I'm so smart. And then times 95. So that gives me, in fact, 475,000 calories. Again, lowercase calories. I only have 3 sig figs, so these last 3 zeros are in fact non-significant. So we see the heat required to bring that you got to extract from the water or from the T is actually 475,000. So that is quite a bit larger than the heat required to melt the ice. So the ice is certainly going to completely melt, and we're going to get the ice tea mixture that's going to be all liquid, but it will be colder. And now we can calculate what the final temperature will be. So here we go. Part B. Anybody have any questions on that before we get started? All right. Looks like everybody's good. So, okay, what we have here is, as I said, Q loss equals Q gain. Well, the hot thing is delivering heat. That actually turns out to be a version of the second law of thermodynamics. Heat on its own accord or spontaneously, in other words, without any help, goes from a hot object to a cold object when they're in thermal contact. Now, that means they could be touching each other. That's the normal way, and then conduction is taking place. Or they could be one contributing heat to the other through convection, or one could contribute heat to the other through radiation. But really, we're talking mostly about conduction. And one of the versions of the second law of thermodynamics, and you should know all the versions, by the way. You'll read them in chapter 20. I'm not going to go over them. That's easy enough. But anyways, in fact, it might even be highlighted on your book on there, because the way I did it, it's supposed to highlight for you, but I'm not sure. So anyways, let's go ahead. The T is going to lose heat. So that's 5,000 grams times 1.00 calories per gram Celsius degree. Again, we still have to have the positive big number minus small number. So really what I'm going to do is, I know the T is cooling, so I'm going to do 95.0 degrees Celsius minus T final. Okay. Now the T is not going to change state or anything, so I don't have to mess with that. But that's all it's going to do. So that's the heat loss. Now the heat gained will be gained by the ice. And the first thing that's going to happen is the ice is going to melt, or is actually going to change temperature. So that's 2,000 grams. And we know it's more than enough to completely melt it all. So I don't have to worry about whether the temperature is just 0. I can just go on and assume it's going to be higher than 0. So that's going to be 2,000 grams times 0.5 calories per gram Celsius degree. And of course, that's going to go from basically -10 to 0. So that'd be 0 minus -10.0 degrees Celsius. That's one term. Now I've got to actually do the latent heat. So I'll say plus 2,000 grams times 79.7 joules per gram. Yeah, that's what I had. Excuse me, calories per gram, not joules per gram. And now I've gotten all the tea, or excuse me, all the ice melted. Now it's acting like water instead of like ice. So I can now say it's going to be 2,000 grams times 1.00 calories per gram Celsius degree times, now the T final is going to be higher than 0, but the T initial is going to be 0. So I'll say, oops, stupid thing. So I'll say T final minus 0.0 degrees Celsius, like that. And all I've really got to do is solve for T now. Now, 5,000 times 1 times 95 is going to be 475,000, which we already figured that out. So 475,000 calories. That's the only term on the left, or that's the first term on the left-hand side. The right-hand side, or excuse me, the second term on the left-hand side is basically minus 5,000 T final. And notice the grams, grams cancels out with the grams, and I just get calories per Celsius degree times T final. So that's the whole left-hand side. The right-hand side is the 2,000 times 0.5 times 0 minus 10 plus the 2,000 times 79.7, which I've already calculated is 169,400 calories. Ooh, that was supposed to be calories back here too. Let me change that real quick before we make a mistake. Okay. So these guys right here are all non-sig figs, but that's calorie as well. That's a lowercase c, even though it looks like uppercase C. And then finally, I got this last term, which is 2000 times 1 times TF. So that'd be 2000 calories per C degree TF. All that. Now the other one's just plain zero, so I'm golden. I can now solve for T final by basically taking the T final that's on the left-hand side and pulling it to the right-hand side. Notice the zero here is what I was saying. When you multiply through by 0, that's going to make 0. So that's why there's no term here. Okay. So I have this term right here, which is T final. I also have on the other side of the equals, which is right here, I have this T final. So if I pull that to the right-hand side, I have 7,000 T final. And then if I take this guy and put it over that side, and this one over that side, I get 475,000 minus 169,000, or excuse me, 169,000. Whoa. Yee, what's up? Did I actually copy an extra 0? Yes, I did actually copy an extra 0. Careful with that. You're not there. Okay. Okay. I'll pull that over there. 169,400. So I'm going to say 475,000 minus 169,400. That actually gives me 305,600. So now I'm going to write 305,600. And of course, that figure is just calories. And then that's going to be divided by 7,000. And that's calories per Celsius degree, like that. So ultimately, I'm going to get 43.6. And actually, the next digit is a 5, so I got to write 2 of them. So I'm going to say it's 43.657. And that's degrees Celsius is the final temperature. Any questions on that? All right. Well, I think that's pretty straightforward. The thing about chapter 20 is, and this is where I'm going to stop for a second sharing this screen. If I can figure out how to do that. Where'd my thing go? There it goes. I'm going to stop sharing this screen. And now I'm going to start sharing a different screen. I'm going to share my book screen. So in this case, I'll share that one right there. Okay. So this was the little experiment I told you about down here at the bottom that Jewel did. Of course, we've already talked about that, but I just wanted you to see it. Now, what I'm going to is I'm going to jump from here because we've basically done everything. I already talked a little bit about the first law of thermodynamics, but here it is. And the critical thing to understand about the first law of thermodynamics is you might not recognize it. If you've had chemistry, you thought the first law of thermodynamics was delta E internal, or they might have used the symbol U, is equal to Q plus W. Well, that's not the way we do it in physics. And here's the reason. What we use is, in fact, and I like to use the D's, by the way. So I'll take it. I'll say that there's a small change in internal energy, also called the thermal energy. And that small change is equal to the small amount of heat added minus the small amount of work done by the system. So that's the key. And that's why there's a negative here. This is work done by your system. And this, on the other hand, is heat added to your system. And what I mean by that is it's positive when heat is added and it's negative when heat is taken away. And I had to put those little bars on there because the D can meet a differential. And on the left-hand side, that's right, because there exists in some sense a D, well, let's write it in black. There exists a DE internal such that you could write a partial of E internal with respect to, let's say, P times dP plus the partial of E internal with respect to V times dV plus the partial of E internal with respect to T times dt. In other words, there's a real exact differential. You could integrate over a path, and it might not even, it could be conservative. So there's independent of path and stuff like that. There's no such function that exists for Q or W. Okay. And also you might notice there's no such function in general for V, but you can, for instance, use the ideal gas law, PV equals nRT, and do that. Just like occasionally we will use Q to be MC delta T or MC dt. So we can do that kind of stuff. But anyways, that's why it's okay to do DE like that, because that's truly a differential. Whereas D bar Q, you can't integrate that to get a Q, but you can assume it's a little itty bitty amount of heat being added to the system. So work done by the system is positive, work done on the system is negative, and then you get back, for instance, the normal positive or plus sign that you would have seen in chemistry. But that's what the first law of thermodynamics is, and it really is just conservation of energy. And in fact, it can be expanded if you want to use, instead of the way I do it, if you want to use like your book does. Remember, I had work in plus U initial plus K initial equals work out plus U final plus K final plus E loss. Your book just did delta U plus delta K is equal to 0. Well, we can do that, and then we can say another version of the first law of thermodynamics is not only this guy, but it's also this guy. And this is partly because of what Joule did. We can say delta U plus delta K, kinetic energy, plus delta E internal is equal to delta Q minus delta W. Okay. So in other words, it doesn't have to be equal to 0, because you can put heat into the system, which would be positive on the right-hand side. And you could do work on the system, which would be negative, but would make that minus into a plus. So that's basically what the first law of thermodynamics is. The second law of thermodynamics, various versions of it, and by the way, they talk about convection, radiation, and conduction. These are just plug and chug formulas that you have to use. That's all I expect you to do with them. Same thing with the calorimetry stuff. And same thing with the efficiency of heat engine stuff that's in chapter 20. So first off, let me show you one version of the second law of thermodynamics. It's the one that I already said to you, which was, yeah, it does show up on here where I highlighted it. The second law of thermodynamics. This is the Clausius statement. Heat can flow spontaneously. Remember, spontaneously means it's going to do it all by itself. You don't have to put any energy or make it do it or anything like that. So heat can flow spontaneously from a hot object to a cold object. Heat will not flow spontaneously from a cold object to a hot object. So in that lab that we did where we heated up a chunk of metal and then put it in a cup of water, a cold cup of water, you could actually use the first law of thermodynamics and show that it's not a violation for you to take that 100-degree chunk of metal, stick it in the water, the water then go from, say, 22 degrees Celsius, which is about what it and the cup was when you first stuck the metal in. What if, for instance, instead the water drop and the aluminum cup's temperature both drop to about 19 degrees Celsius from 22, and then the heat from that actually went into the metal and made the metal go up to 200 degrees Celsius. Okay, or let's say 180. Okay, that is actually, if you worked out the numbers appropriately, you could make that not a violation of the first law of thermodynamics, but it is definitely a violation of this version of the second law of thermodynamics. But that's just a very specific process, so we need some other versions. So there are other versions, and one of them involves a heat engine. And the way we imagine a heat engine, which is like a car engine, for instance, a diesel engine, you push gas into it. The gas then absorbs some heat, or actually I should say the engine takes some heat from the gas, because what happens is the engine squishes the gas to such a high decrease in volume that it explodes even without a spark plug. Whereas if you did a regular gas engine, the compression isn't as big. It's only like a factor of 2, whereas it's like a factor of 5 or 6 with a diesel. So you actually have to use a spark to cause it to ignite. But when you compress that diesel so much, the diesel fuel explodes. That creates heat, and that heat is drawn from that to push a piston. That's the work. The piston rolls up away from the explosion, turning the crankshaft, and the crankshaft can be used to turn the rear axles. And then, of course, another cylinder will do the same thing, so it can keep going continuously. But in the process, once that's expanded, then the piston gets pushed back down by one of the other pistons that's coming up, and it expels that gas left over out into the environment. And that energy that is still higher than the energy the gas had when it came in, that's spit out to a colder temperature. And the efficiency of such an engine, all engines, including the Carnot engine, is basically what you get, which is the work, divided by what you pay for, which is the H. Well, if you'll notice that QH supplies everything, so QH is actually equal to W plus QL, which means W is equal to QH minus QL. And then this over QH, well, that gives you 1 minus QL over QH. And you see the efficiency could never be 100% unless the thing gave off 0 heat loss. The QL would have to be 0. So it's never going to be 100%. But if you make a Carnot engine, which gets rid of friction, it makes it conserves entropy because it makes it a reversible process. Time's running out here. I'm just going to finish the sentence, but if you need to leave, go ahead. But anyways, we can show that for the Carnot engine, the efficiency turns out to be 1 minus TL over T hot. So that's another equation you should be able to use, as is these, and they're just straight plug and chug equations. Okay, but the deal is, another version of the second law of thermodynamics is that no heat engine can run as efficiently as a Carnot engine. The Carnot engine is a maximal efficiency engine, and nothing can run more efficiently than that. So if you ever find someone claiming that their efficiency, even if they don't actually come out and say it, but if you do the calculations like it does in these examples, and you find that the efficiency of the engine someone's trying to sell you is more efficient than the Carnot engine, then you can just know that they're violating the second law of thermodynamics, and they're what we call snake oil salesmen. This is your author going through the process of deriving it. One of the equations they use, by the way, is P1 V1 to the gamma equals P2 V2 to the gamma, where gamma is equal to the molar specific heat at constant pressure divided by the molar specific heat at constant volume. And there's even some equations from that says like E internal is related to CP and CV and all that good stuff. So those are equations you're expected to use as well. But anyways, in the end, he does find that the efficiency is TL over TH. That's got to be done in Kelvin though. So no device is possible whose sole effect is to transform a given amount of heat completely into work. That's another version of the second law of thermodynamics. So, just go through this chapter and look up all those and look at these examples. They're pretty much as hard as it gets for anything I give you on the final. If you guys need to, like I said, you can set up a meeting with me tomorrow. I could come to campus, or I could just set up a Zoom meeting for you at any time tomorrow. I might be able to find some time Saturday and or Sunday. I definitely could find some time Monday. In fact, Monday I'm going to be on campus. I will be there by probably 8 in the morning, and I will be there till probably 3 in the afternoon, at least 2:30. But it's all optional. My students don't have to come to it, but I will be either in my office, which is JC24, or one of the labs, JC21, JC26, or JC12 or JC13. So it's all on one hall. You'll see me, so you don't have to worry about memorizing those numbers. And my office has my name on it too, so you can find that. But just come. If you make an appointment, then I'll make sure I let you know where I'm at so you can find me. But that's all time available to you before the test. Just let me know if you need anything. Do not try to contact me via email, though. There's a high likelihood that I won't see the email in time, so it's better you just go ahead and straight up text me. I will stop sharing, and of course, everybody, like I said, you are free to go. Feel free, like I said, to text me if you have any questions. That's the best way to get up with me, at least through Monday. And remember, your exam is Tuesday. You're supposed to start it no earlier than 4:35. I have a couple people that might be starting it earlier at the testing center, and I have one person that's going to start it later at home. But you have to use Respondus Lockdown Browser and Respondus Monitor, and there should be a version of the practice test for that, so you can make sure you're up to speed on it before you have to take it. I'll wait for the last person to leave, and you guys have a wonderful weekend. Study a lot of physics, do physics every day. That's the best way to live.
Thank you so much.
Thank you. Thanks for coming, everybody. Sorry to blow through that so fast.
Thank you.
You're welcome. Thank you.
Just letting you know, I just got an email back from the testing center, and it looks like I should be fine.
Yeah, cool. Good deal. So you think you can do it at the time on Tuesday, or at least on Tuesday sometime?
Looks like it. Like, how much time would I?
You
How
only
much
need
time
2
would I
hours.
have for the?
I'm
About an
allowing
hour?
you 2 hours. Nobody ever takes 2 hours. I mean, if you're that person that normally takes the full time, then definitely account for that. But generally speaking, nobody ever takes the 2 hours. And sometimes, well, the testing center has very strict rules. Like if your test is supposed to take 2 hours, they won't let you start it unless it's at least 2.5 hours before closing. Like there's a rule like that, and I'm paraphrasing, so it might be slightly different than that rule. So make sure you check that out. But they might let you elect to take a smaller amount of time. I always tell them that that's okay with me. So I'll set up the testing center thing. I'm just supposed to do it 24 hours in advance. So I'll try to do it today or tomorrow.
Well, if I don't need 2 hours, then it should be fine, since I have it scheduled to start at 4:35. So
Okay,
about an hour and a half.
that's cool. What's going on after? Do you have to be somewhere, or are you thinking about lab or something?
I was gonna take my lab test earlier,
Okay, gotcha.
so
I was just making
yeah.
sure you weren't trying to think that you had lab that day. I know you don't have lab, but you might have the lab test or something. So
No, it's the lab test is available and it's on Canvas, so I can take it pretty much whenever I want, so long as it's before the end of Wednesday.
that's cool. No problem. All right. Well, I'll set it up. It looks like I have 2 people for the testing center. So that should be fine. I'll set that up and let me know if you need anything. And like I said, the best way to contact me is definitely via text between now and Tuesday.
All right. Well,
All right.
have a good weekend.
You too. Take care. Bye-bye.